Yeah, so we're on the Hawkesbury campus of Western Sydney University, and we're in a high-tech glasshouse here. It's one of its only kind in Australia. And in particular, right now, we're in a 420 square metre production bay. And to the side of me, we've got 8 research bays. They're all 105 square metres. And what really makes this glasshouse high-tech and one of its kind is that it's completely computer controlled. So in this bay right here at the moment, this is our teaching bay. So we're growing capsicum varieties here, where students come in and get engaged to look at how fertigation can affect crop growth on capsicums. But in behind me, as you can see in the red film, that's a polycarbonate film that's been lined on the roof and on the sides of 2 of our research bays. And what it's doing is it's providing more of the red wavelength of light. So it's removing the green, translating it into more of a red, and it's also diffusing the light. So different parts of the crop canopy can get exposed to that light as it diffuses through. And essentially the combination of more red and more diffuse light can enhance growth. Behind that, we have 2 bays of our light altering film that's got a bluish tinge to it. And it's in the second generation, it's a little bit less blue now. And what that film's doing is it's blocking out some of the UV and a bit of the infrared in order to keep out the wavelengths of light that often cause heating within a glasshouse facility. But you've got to be careful when you're changing the spectrum of light coming through in films, whether it's appearing more red or more blue. You can also alter the metabolism that's occurring and the product quality. So it's important that you check that the post-harvest attributes of the crop is not altered. In designing the first generation of film, there was a bit of a reduction in overall light transmission, and it stole a little bit of the blue and the red wavelength of light. So in its second generation, we've sort of re-engineered it to bring back some of that red and that blue, and a little bit of the ultraviolet and far red, but also while still hoping that we can reduce the light energy that comes in that causes heating within the glasshouse. And behind that, we have our control bays where we don't have any film, so that we can compare between the red light altering film with the blue light altering film versus the control. So at the moment, we've got 2 PhD students and postdocs, as well as engineers, working together. The new 3rd generation leaf film and 2nd generation blue altering film. What we're hoping to do is understand the relationship between light capture that enables photosynthesis and carbon production to that of photoprotection, which is understanding how the plants protect themselves on sunny days. And that relationship we've found in our first few studies seems to be linked. So we're trying to understand how these processes are coordinated with the end goal of trying to essentially keep the plants on steroids, keep them at maximum growth, whether it's a cloudy day, sunny day, whether it's autumn, spring, summer, winter. We can maintain photosynthesis and the plants can protect themselves when necessary. Unfortunately, these films are reducing photosynthesis to some degree, at least the blue one, and they're also affecting photoprotection, where the red film appears to be enhancing photosynthesis to some degree. So we hope to get into those mechanisms a bit more, and that will hopefully, down the track, lead to the engineering of films that could be almost seen like a chameleon, where they can change their spectrum and characteristics depending on whether it's a bright sunny day like right now compared to maybe in days to come being a cloudy day, and they can shift those spectrums of light. That would be the end goal down the track. So ultimately we've got to get a fine balance between the film, the energy use efficiency, and whether you're seeking a gain in productivity or the nutritional value of the crop.
Glasshouses use large amounts of energy to maintain a stable temperature, and Professor Chen says even a small energy saving can yield big dividends for growers.
As you probably know, there are 2 biggest costs in the protect cropping industry. The first one is, of course, the labor, then followed by the energy. So by reduce even 5% of energy from protect cropping, that will save millions of dollars for the growers. So we actually have already got some companies showed interest. So I think we have shown some promising results, particularly for the leaf film. And those films are very flexible, can be adapted to not only the high-tech greenhouse you can see here, they can also be directly applied to the mid to low-tech greenhouses or polytunnels. So I can see the potential use by growers in the near future.
And can you apply it to existing protected cropping systems, or is it only on new builds?
Those can be applied for on the existing ones. For example, as you can see here, the leaf film is actually attached to the glass house. So of course this was built before the leaf film was applied. And for the lower tech greenhouses or polytunnels, yeah, they can apply it on top of the existing coverings, or even put it inside, depending on the requirement of the grower.
And do you think it can be a challenge to commercialise this kind of technology?
There are challenges, particularly really I think the grower want to see the actual cost benefits. So that's why we have a team of researchers from the School of Business at Western Sydney to look at the life cycle assessment, to look at potentially how this gonna bring if the growers invest to purchasing those films in their greenhouse, and whether they can get more benefits or more economic returns. Of course, those need to be tested. There are challenges, but I think it's also promising because those films are not that expensive, and if they get promoted broadly to many growers, then the cost of those films will be reduced further.